In addition to the uh, molecular geometry and electron distribution that we can see as shown previously, we can also get some great insight into the atomic orbitals or molecular orbitals of a molecule. And we can see those by doing a molecular orbitals or a natural bond orbitals calculation. I picked a couple of really simple molecules to help reorient you on different types of molecular orbitals. The first one I want to look at is a sigma type molecular orbital, where the electron density exists along the axis between two nuclei, and the shared region of electron space and the density is directly between the two atoms. A good example of that is the hydrogen molecule, which is in every general chemistry textbook. Two 1s orbitals come together, one from each of the hydrogen atoms, to form an overlap and region between, which results in a bonding orbital, shown here in red, and they negatively overlap, resulting in this anti-bonding orbital, shown in yellow and green. It's important to note that WebMO has a color scheme where any filled orbital gets a red and blue coloration, and any unfilled orbital gets a yellow and green coloration. In addition to that, I want to remind you that as you increase in energy from one orbital to the next, you actually increase the number of nodes. There are no nodes in this bonding orbital, and in that region where there's no overlap in the anti-bonding orbital, there's a nodal plane. Additionally, we're going to add some new nomenclature. Rather than simply referring to this as a bonding orbital, we can refer to it as a HOMO, or the highest occupied molecular orbital, because both of the electrons of the s orbitals used to make the bonding orbitals are placed into it, making it the highest one occupied. Next higher in energy is the lowest unoccupied molecular orbital, or LUMO. And the big important thing to learn on this slide is that we can see sigma type molecular orbitals by finding their electron density between the two atoms or along the axis of a chemical bond. Another classic system that is presented in every introductory organic course is the allyl cation, which consists of three carbons bonded together by a double bond, and one of the carbons being a carbocation. It exists as two resonance forms that can be drawn placing the carbocation on either of the terminal carbon atoms. I optimized the geometry using Gaussian 09 through WebMO, and you'll notice we have a nice symmetric structure about the center carbon. WebMO shows one of the bonds being a single bond and the other carbon-carbon bond being a double bond. But if you look closely, you'll notice they're the exact same bond length, which tells you that even though I drew the species as the molecule on the right over here with a double bond on one side and a single bond on the other side, the computer program is smart enough to realize that these carbon-carbon bonds actually have the same bond order, and it makes them equidistant. And really, the single bond and double bond depicted is just for us to feel comfortable with Lewis structures. Most important thing here is the bond distance itself. You should also notice that the structure is nicely planar. This should be a good hint in the future that when we have a pi bond from our double bond and a nice planar structure, that we're going to see some conjugation, which is exactly what we do see in the allyl cation. An NBO calculation can be done to look at the atomic orbitals at each of those carbon atoms, and we see this nicely symmetric lobe of a p orbital above and a lobe of a p orbital below the plane of the molecule. And at each carbon atom, we can see the same sort of p orbital. When we see a set of atomic p orbitals like that that come together, they're going to create a nice manifold of pi symmetry molecular orbitals, the lowest energy of which here is red and blue, which is WebMO's way of communicating to us that that is a filled orbital. There are two electrons in our allyl cation, two making the pi bond, and none at the carbocation center. So those two pi electrons will fill this lowest energy orbital. The two higher energy orbitals are yellow and green, indicating that they're unoccupied. And as you see, we go from no nodes in the lowest energy to one node in the middle and two nodes in the highest energy orbital. And since we have two electrons in the bottom one, we'll use that same nomenclature we did on the previous slide and label that as the HOMO, or highest occupied molecular orbital. One higher than that is the LUMO, or lowest unoccupied molecular orbital. And very cleverly, the one just higher in energy than that is the LUMO plus 1, And if we were depicting another orbital, it would be the LUMO plus 2, etc. Any orbitals lower in energy than the HOMO we refer to as the HOMO minus 1, and then the HOMO minus 2, and so on. For future reference this semester, if you encounter an orbital that has exactly one electron in it, that's referred to as the SOMO, or the singularly occupied molecular orbital. Now that we've sort of reacquainted ourselves with sigma type and pi type molecular orbitals and p atomic orbitals, let's take a look at two really simple cases. One is the water molecule, which is common to every Gen Chem textbook, and the other is anisole, which I would argue is just like water because it has an oxygen bonded to two things, as long as you can replace a hydrogen with a phenyl and a hydrogen with a methyl group. So for the water molecule, it should be easy to optimize. It should give us a nice familiar structure that we're all comfortable with. We've all memorized somewhere along the way that the HOH bond angle is about 104.7 degrees for water. VSEPR, which we learned in general chemistry, would indicate that we have an oxygen atom in the center with two bond pairs, one to each of the hydrogens, and two electron lone pairs around it, giving it 4 regions of electron density, which would indicate that it has an sp3 tetrahedral type electron geometry and a bent molecular geometry. The nice thing about these sorts of quantum chemical calculations is we can actually visualize those lone pair orbitals, which I did by doing a natural bond orbitals calculation. And these are displayed right here. I have one orbital that looks like this, and the other that looks like this. And I kept the orientation of the HOH framework the same so you could see the relative positions of those orbitals. These orbitals look nothing alike. If you look at one, we see a clear symmetry of an orbital above and below the plane of a molecule, which is definitely a p lone pair, and I confirmed that using the NBO output. There's some instructions in the lab manual on how exactly to interpret those outputs, and you'll get some experience with that in Chapter 5. The other lone pair seems to have its electron density mostly confined to one lobe, and it seems to be along the axis between the two OH bonds, sort of aimed back into the screen. And I got the information from WebMO that that's roughly an sp lone pair. This should seem really odd. If VSEPR was correct, and the oxygen atom in the water molecule was an sp3 hybrid, we should expect to see 2 sp3 hybridized lone pair orbitals on that oxygen atom, neither of which is actually present. It turns out that while VSEPR is great, this is a really good indicator that the predictions of VSEPR are not perfect for predicting hybridization. And we can see that just by looking at the orbitals of the water molecule. They actually get the geometry pretty reasonably well predicted. It turns out the electron geometry and what's happening with what orbitals the electrons might be in isn't super well predicted by VSEPR, and you're going to see that again in the case of anisole over here. I optimized the structure, and then I ran an NBO calculation very similarly, and you'll see a very familiar shape to this orbital for the oxygen lone pair that looks a lot like the sp lone pair on a water molecule, and one here that looks a lot like the p orbital on a water molecule. And so in that sense, the electron locations for the orbitals in the anisole is very similar to that of the oxygen and water. The big importance of this in regards to organic chemistry is that oxygen has a pretty big effect on the aromatic ring adjacent to it. And we see that in things like NMR chemical shifts. We see that in Friedel-Crafts or other electrophilic aromatic substitution reactions, where the electron density of the ring is really important. And in this case, once we have an oxygen nearby with a p symmetry orbital like this, it's actually perfectly positioned to conjugate with the pi system of the aromatic ring, which results in a molecular orbital of this type, where we actually see an overlap of the p orbital from the oxygen with the pi system of the aromatic ring to have a delocalized system that runs all the way through the aromatic ring and back to the oxygen. And one of the huge takeaways from this slide is that VSEPR isn't perfect. It's a pretty good first step, but in any case, where there's a lone pair adjacent to a pi system, VSEPR is not going to do a great job of predicting the location of those electrons at all. And you really need to be thinking about the fact that a lone pair next to a pi system is going to conjugate, and you're going to get some electron overlap from that p orbital into the aromatic ring. Another cool thing that we can get out of computational chemistry is a potential energy surface. And this is actually an example from some of my research, and I did these calculations as part of a project that I was working on. We were really interested in looking at this molecule, which is called diazurenone, which is a ketone with a diazo group attached to it. And so you put those together and you get diazurenone. It's this tiny little species combined of a carbon monoxide and a nitrogen molecule stuck together. Both of these molecules are probably widely abundant in most molecular clouds in space, and they've both been detected in many regions. And if you put those together, you could imagine that it might be possible to make a molecule like diazurenone in space. And so one of the things that I did is tried to understand how easily it would decompose. So I calculated a geometry and energy for the reactant, in this case diazurenone. I calculated an energy for the transition state, which is that moment that exists for just an instant where we have a structure that could go toward the reactant or toward the product at the top of that potential energy surface hill. And the energy it needs to acquire to get up there is about 25 kcals per mole, which is a pretty reasonable barrier to decomposition. And if somehow diazurenone was able to form in the interstellar space, it would be cold enough and isolated enough in the vacuum of space that it probably wouldn't readily decompose. But if it does decompose, it releases a tremendous amount of energy, all the way down to what I labeled as 0 kcals per mole here. So it loses 91.8 kcals per mole of energy, which is a tremendous amount of energy, as it breaks apart into two of the most stably bonded molecules in the universe, carbon monoxide and nitrogen. We can get some cool insight into how this reaction goes, and I actually made an animation of the reaction over here showing that the carbon-nitrogen ring is not broken symmetrically. One carbon-nitrogen bond breaks before the other carbon-nitrogen bond, and the CO sort of pops off as it slides to the side. This is kind of a cool bit of insight you can get from computational chemistry. We won't be doing these types of videos in Chem 344 as part of the required bits, but there is an optional bit as one of the exercises today that will allow you to sort of visualize a reaction in this way. We will be calculating a transition state. And the important thing to know about a transition state compared to a reactant or a product ground state is that at the transition state, this motion of the carbon atom from being bonded to both nitrogens to being not bonded to both nitrogen is a negative or imaginary vibrational mode. And it corresponds to that motion that takes place for one molecular vibration in which the carbon pops off that ring. And the characteristic of every transition state is that they have exactly one imaginary or negative vibrational mode. And later on, you'll learn a little bit more about how to calculate those vibrational modes and get that insight. All of your minima, or stable reactants and products, have 0 negative or imaginary vibrational modes. All of their vibrational modes are real.